Welcome to Textbook Engineering Problem, where we explore complex engineering problems and discuss different methods for solving them. In this video, I'll be breaking down a problem and discussing different ways to tackle it. However, keep in mind that there's no one correct path for some of these solutions, and I encourage you to share your own insights and thoughts in the comments. Together, we can learn and improve our problem-solving skills. So sit back, grab a notebook, and let's dive into today's problem. Today we're working out of Elementary Principles of Chemical Processes, 3rd edition, and we're doing problem number 4.55. The problem statement says, a complex solution A contains up to 10 weight% of a drug R. Mass fraction, they say, is XRA, and it's, yeah, we know what a mass fraction is. Okay, a stream of this solution is the fresh feed to a continuous pharmaceutical process. A portion of the fresh feed goes to a reactor in which the single pass conversion of R is 99%, and the remainder bypasses the reactor and combines with the reactor effluent to form the final process product, P, which contains 0.75 weight% R. The bypass fraction is F, kilograms bypassed by kilograms fresh feed. A second mixture, B, which contains no R, is fed directly to the reactor at the same rate at which A enters the reactor. Okay, a little complicated. I probably make it look a little worse than they do in the book. They've got a similar picture in their book, but the difference is that I labeled stream 2 and stream 5 to make it easier to calculate what these mixing point values were. Here and here. Okay. So I find that helpful. You don't have to do that, but I find it helpful. Okay. So part A, it says, without taking a basis of calculation, draw and label a flowchart. Okay, so we did that, but they also gave us one. So, I mean, you could just copy the one they have in the book, or you could do this. Then write the system equations for the product, mixing point, that's this point right here, and the reactor, so that's just a box around the reactor itself, not around the whole process, so it doesn't include this bypass stream. Okay, and the reactor, and prove that the process has 2 degrees of freedom. You should be able to convince yourself that balances on the bypass splitting point yield no additional information. Yeah, so they wouldn't yield extra information because what they mean by that is the equations that you get from those would not be independent of the other equations. Okay. Yield no additional information, and if balances on the reactor and mixing point are satisfied, the overall process system balance must be satisfied as well. Yeah, so if the other ones are not independent, so if you have a certain amount of degrees of freedom that are all satisfied in this point and around the reactor, if you have that satisfied and the other equations that you can write are not independent from those 2 points, then yeah, of course, the whole thing will be satisfied, obviously. Yeah. Okay. All right, so let's finish up with part A. So we did our flow chart and labeled the flow chart, so we got that there. Now we're doing the material balances for the mixing point. Okay, so we can do our overall balance, and then we can do our R balance. Okay, so the overall balance is pretty easy. We've got a certain amount going in and a certain amount going out. And this is just for the mixing point, again. Then you have a certain amount of R going into the mixing point and a certain amount of R going out of the mixing point. Okay, so when I did my balance, I understood that this was known, but then reading through the problem later on, I realized that they were saying it was up to this, so this is the maximum it could be, but they're not actually specifying and telling us what it is. So that is another unknown that we don't know. Okay. So I calculated that we had 2 unknowns. Even if we knew what this was, we had 2 unknowns in the mixing point, but we only have 1 unknown given the specs that we've got here. We only had 1 unknown in the reactor balance. So this is the overall reactor balance, and then this is the reactor balance around R. I calculated that we only had 1 degree of freedom here. we would have 2 degrees of freedom if we didn't know what the mass fraction was going into the reactor. So so we wouldn't know what this value was, so that would be another unknown. Okay, so that there are 2 degrees of freedom. Okay, so there are 2 degrees of freedom for both of these processes. Okay. Part B, suppose that MP is equal to this value, which is our M4, and that the mass fraction going into the reactor is this amount. Now, when I went through and I solved this, this reactor amount is, and then if you look in the range that in part C, they have a range that you're supposed to calculate XRA from. You can solve what this is, but it doesn't actually end up making any sense, because in order to hit this small of a fraction going into the reactor, you would have to bypass like your entire stream, or more than your entire stream. It doesn't make sense. It's kind of like out of bounds of this reaction. So you can specify this, but it doesn't. It makes no physical sense when you get it that low. So what I think they meant to do is to solve it for this value, for 5%. So you can do that this way, and you'll still end up getting the same. You'll still end up getting like real numbers if you use that value, but yeah. So I used this value. So those are some of the heads up on this problem. I'm not sure that they meant to do that, or I could be wrong. I don't think I'm wrong, but I could be wrong. So if you guys want to check that out and see if you get some real results with this value, let me know and I will post a correction. I was not able to find how that works, but if you spot a mistake in my algebra or something, which is really easy to do on these kind of problems, just let me know. All right, so now we're going to take all of these equations that we wrote up here, right, and we're going to use this equation set from the overall balances, and then we're going to use this equation set from the reactor balance, and we're going to try and put 2 equations together with 2 unknowns, and the unknowns, because they told us in part B to calculate M1 or M naught, that as they have in their problem, and the feed rate. So M1 is M naught in my notation, and not the feed rate, the fractional amount that splits off at this mixing point, or this intersection. Okay, so F. So we'll get 2 equations with 2 unknowns, the 2 unknowns being M1 and F. Okay. So first off, I start off with an overall balance, and then I just start substituting in variables that we know relate back to M1 and F, and I'm going to try and get rid of all of the extra stuff that we've got in here, like the M3 and the M2. So I just highlighted the ones that all the unknowns, and then I tried to substitute in variables that I could eventually relate back to M1. So we know that M2 is equal to M5, and M5 is related to M1 and F. Okay, so we can just substitute that in, and then M3 is also related to M1 and M5. Okay, so we can then do all of our substitutions to get rid of all of those extra unknowns that we have. So now we just have one equation that is in terms of M1 and F. Okay, that was over on the overall balances. Now we need to do balances on the R component. So starting from here, now we do our independent equation is going to come from all of our information about the flow of R and the consumption of R. Okay, so now we start off with this information, because we know what MR5 is, and we don't know what MR2 is. Okay, so then we just begin our route on substitution here. You guys should be pretty familiar. Here are some of the These are some of the key equations that we need to know for substitution, okay? And then we basically put it all in terms of M1 and F here, and then we do a little bit of fancy crunching numbers and things like that. Now, these equations, 1 and 2, are a set of 2 equations and 2 unknowns, and we can solve those just by using more substitution, or you can use linear algebra at this point, and solve for those variables. Okay. So when I solved it, when I solved this, I got an F that equals 1.2, basically, and then M1 equals 6.068. Okay, so that would be kilograms per hour, and this is a fraction. So it doesn't really make sense, right? Because the fraction shouldn't be, like, the amount of F that is leaving, you can't have more, the F cannot be greater than 1, obviously, right? Because then you would have more flow coming out here than you have going in. That would mean you have to have, like, flow going from the reactor or something, like getting sucked out this way or something like that. Like, it doesn't make sense to do that. So I don't think that is physically possible. What they have written, like I was saying earlier. So I mean, that's the answer that I got. It doesn't make any physical sense to actually do that. But if you remove the value, and if you change that to instead of being 0.5%, and you change it to 5% instead of 0.5%, then it becomes real. So then F in this case equals 0.254, and M1 equals 2778 kilograms per hour. And that makes a lot more sense. Okay. But like I said, if you spot an error in my calculations, just let me know. And we can work on posting a solution or pointing out the spot where we need to look closer in the comments. I'll pin the comment. All right. So now it says you can make a chart of F versus WR1 using a computer software. I did they said easy solve parameter. Let me go ahead and read the problem statement. The desired production rate for MP and the mass fraction of R in the feed both vary from day to day. Use an easy solve parameter sweep to generate a plot of F versus XRA for the MP equals 4,850 kilograms per hour and XRA varying between 0.02 and 0.1. Prove that you would get the same curve regardless of the value of MP. Okay, so we're plotting a function. I plotted this function. It looks something along the lines of this. You should get something that kind of looks like this, where this is F and this is WR1. Okay, where it ranges from about 0.02 to 0.1. Okay, so you should get something that looks like this. It's nonlinear, and this is the function, right? I just got this function by combining our 2 equations, 2 unknowns. Just combine those together, and then you can solve for WR. So you don't have to necessarily use the easy solve sweep thing that they're talking about, but you could just use this equation and plot it. However, it does help to have a computer to help solve some of these problems, and obviously to plot it helps. So you're welcome to do that as well. I did not do it in this case, but anyway, you can see that in this equation, we were able to remove M4, even though it was in these equations to begin with, right? So we were just able to remove it through substitution. So yeah, it does not depend on, this relationship does not depend on M4 because we can remove it. Okay, so that is it for problem number 4.55. Thank you for watching, and I hope you found this video helpful in your problem-solving journey. Remember, there are other routes you can take to arrive at the same correct answer, and I encourage you to leave a comment with any additional insights or questions you may have. Also, if you have any specific engineering problems you would like me to cover, please let me know in the comments. Your feedback is valuable, and I look forward to continuing the conversation with you. Don't forget to like and subscribe for more engineering problem-solving videos. Thanks again, and I'll see you in the next video.